welcome Kathy Malan, who is a postdoc at Niels Bohr Institute, Copenhagen. So Kathy did his master's and BSc from Delhi University, then did his PhD at University of Strasbourg with Rodrigo Ibata, then had postdoc positions at Stockholm University, and then the prestigious Humboldt Fellowship at MPI Heidelberg, and now is a postdoc at Niels Bohr Institute, Copenhagen, Denmark. So Kathy has done a lot of very interesting work on galactic archaeology and studying the Milky Way, providing more insights on dark matter and other stuff. And uh, today is going to talk about this his very famous work on Shiva and Shakti, which has got a lot of press. So without further ado, Kathy, please take it away.
Yes, thank you, Shantanu, so much. And hello, everyone. It's a pleasure to be here and talking and discussing this topic with all of you. So what you're seeing on this video are two stellar populations in magenta and green, which we named Shiva and Shakti stellar populations. And these were identified in the Gaia data. So our current understanding is that Shiva and Shakti are two distinct stellar populations that came into the Milky Way about 12 billion years ago. And this is their present day distribution in the very inner regions of the Milky Way. So this is the statement and the result, and this is kind of the crux of the presentation. But of course, you cannot understand or you cannot appreciate this result alone in its full detail if it's not put into some context, right? So you need some context. And that context is that this result that I will be sharing with you today is just one piece that we have fit into a much bigger puzzle of trying to understand how did the Milky Way galaxy form. Or you can even make this puzzle even broader by asking a question, how do Milky Way-like galaxies form in our universe? So this is just one of the paper or one of the pieces into that bigger puzzle that we're interested to understand. So at the outset of this presentation, I would also say that the agenda is not really this one-sided communication of this result. That's kind of my sub-agenda. The main agenda, at least for me, is I hope to be able to, through this presentation, I hope to be able to excite you about this field of Milky Way formation, or as we say, galactic archaeology, which is a very young field. So it's only a few decades old. Which is a very flourishing field. There are lots of opportunities, and there's lots of creative work happening, and there's lots of funding available, jobs available, and so on. So this is a field which basically I joined in 2015, and there are lots of interesting astrophysical surveys. So despite of whether you're interested in theory or in observations or in running n-body simulations, and if you're interested in programming, this field is kind of interesting and could be, you may like it if you give it a try. And so I know that at least in India, not many institutes are invested in this science. I personally know a few colleagues who are working on the similar field in IIA Bangalore and also at Delhi University. I'm sure there are other people and institutes also involved, but one of my hopes is also to see more and more papers and more science being done in India in this field that now I'll share with you. So the bigger context of this presentation, so I'll come back to Shiva and Shakti later now. I think it's important to give you a kind of context of where this result is going, or where this result fits into the bigger picture. So the question is, how did the Milky Way form? Which is an interesting question, because we look at our home galaxy. Milky Way is our home galaxy. So of course, you look into the sky, you look at the Milky Way, you ask, okay, so how did this present day assembly of stars and structures came into being, which is a valid question. That's how any science or philosophy starts. And so people who are kind of interested in this question are called, people like me are called galactic archaeologists. And our ultimate goal is really to be able to run this multi-dimensional star by star movie, where we basically start from some initial conditions for stars and gases and dark matter and so on, and we play this movie forward for 13 billion years and so, and hopefully that assembly would kind of match the present day distribution of stars. So that's the ultimate goal. And when I say multidimensional, it encodes the phase space measurements of the stars, it encodes the ages and chemistry of stars as well. So of course, then you can ask that what's so special about the Milky Way? Of course, we have other galaxies in the universe as well, and we can ask the same question for those galaxies. So we can ask that how did the Andromeda galaxy form, or how did Sombrero or M64 form? And you're quite right, and that's exactly kind of what HST and JWST programs are doing. But the advantage of asking this question of galaxy formation for the Milky Way is that it is only in the Milky Way where we can resolve each star, and for each star we have the measurement or their understanding of their age for a star, the orbit of the star, and the chemical composition of a star. So this is something that we only have for our home galaxy purely because the stars in our galaxy are closer to us. So of course we can resolve each star compared to stars in galaxies further out into the halo. So what Yes. So what I mean is that for most of the stars, for millions and billions of stars, we have the information of, for instance, okay, for this star, I see we have a measurement, kind of a measurement of its age, metallicity, and okay, it's moving in this direction. If I look at that star, okay, I know that it's moving in that direction. The disk is kind of rotating and so on. This is a very artistic impression, conceptual picture, just to give you an idea that this is the advantage that we have. And once we have such wealth of information for the stars in the Milky Way and with such detailed measurements, then we can really try to understand the very intricate processes and very delicate processes involved in the formation of a galaxy, which is very, very difficult to do for galaxies, for other galaxies in the universe. So this is going to be the kind of the outline for today's presentation. First, I'll spend some time trying to describe the structure of the Milky Way, which is hopefully would be a pedagogical introduction to this topic. And I apologize in advance if I end up over explaining things or under explaining things, because I'm not 100% familiar with the diversity of expertise in the audience. So please bear with me. Then I'll move on to asking this question of how did the Milky Way form, and trying to compare our understandings from the models and from the observations. And particularly, I'll be paying attention to the observations from the Gaia satellite, from the data we have from the Gaia. And then towards the end, I would then move on to talking about Shiva and Shakti, because I think only after this pedagogical introduction, it would become more easier to understand. Right, so this is what the Milky Way looks like. And please note, this is an artistic impression. So for instance, we of course are sitting, we are in the frame of reference of the sun. So we are not at the center of the galaxy. We are at the sun, which is about 8 kiloparsec distance from the center of the galaxy, moving at a speed of about 225 kilometer per second. And the mass of the sun is of 10 to the 30 kgs. And I think this is important because all the measurements of masses that we that we make for the galaxy is in solar masses. Right. So I think this is important for this presentation or any astronomy presentation. It's important to understand that we are making measurements from the heliocentric frame, from this frame, which is at 8 kiloparsec from the distance and is also has a motion in it. Then we have at the very central region, you have lots of stellar density, and that's the bulge or the bar, which has a size of about 3 kiloparsec. Over here, then you have a distribution of stars in the form of a disk that you're seeing, which has a size of about 20 kiloparsec, mass of about 10 to the 9 solar masses. And then you have a galactic halo, which is made up of both stars and dark matter, so baryons and dark matter, which has a mass of about 10 to the 12 solar masses. And the extent of galactic halo, even though we have not measured it because we cannot observe dark matter, so we cannot observe the extent or structure of dark matter around the galaxy. But from the models, we have a prediction that maybe the dark matter halo surrounding our galaxy, its extent to about 100 to 200 kiloparsec or even beyond. But of course, so the question is, how do we know even those things about the galaxy that we have not observed? And that's coming from both the models of the Milky Way and the observations of the Milky Way. So first, I'll spend a few minutes talking about what do I mean by the model of the Milky Way. So what we have are the models of galaxy formation in the lambda cold dark matter cosmogony. So maybe you're familiar with the lambda cold dark matter model. And what we want is to be able to have this n-body model, evolving model of how a Milky Way-like galaxy form. And so, what many collaborators worldwide, many scientists have done it, is they have given uh, our current understanding of the cosmic parameters, so things as Hubble constant, and our understanding that fine in the universe, 27% is dark matter, 5% is visible matter, 68% is dark energy, and all of this cosmic understanding is fed to the computer, a supercomputer, of course, because we are trying to simulate a kind of entire universe. It's 14 billion years of evolution of structure formation, which actually happens over a real time of about 4 to 6 months. 6 months. So for a 4 to 6 months, you just let a computer sit, you babysit it, kind of ensuring that the simulation is running nicely, and finally, what you get is a movie of the evolution of how structure and galaxies form in the universe. So this is what one of those movies looked like, for instance. So it starts at when the age of the universe is about 0 billion years old, so just when it started. And this is the movie that you're seeing is just dark matter only movie. So it doesn't have baryons, doesn't have gas or stars. And so the high density regions are basically higher in contrast, and immediately you start to seeing these dark matter filaments, right? So each node is kind of a small galaxy or a galaxy, or a dark matter halo, and you see these dark matter filaments along which the material gets accreted into the main halo that will start emerging at the very center of the video, uh, that you're seeing over here. So you see a Milky Way like halo, a dark matter halo would start emerging at the center, which is being fueled by the accretion and merging of these smaller dark matter filaments, or smaller dark matter substructures that are coming in and forming, leading to the formation of this inside out growth of Milky Way like halo, right? And so the other thing to also note is that the galaxy then does not end up being a smooth distribution of matter. It's highly structured, right? As you can see. But of course, this is just dark matter, something we cannot observe in the galaxy or in the universe. But this is what the model is predicting, that this is how the galaxy formed and that it's highly structured in terms of dark matter. So this is the dark matter only simulation. But we can also add baryon. So here you are seeing how the gas evolves in a Milky Way during the formation of a Milky Way like galaxy. So slowly and slowly, you would see this gas is being accreted. On the left lower panel, you can see how the stars are evolving. So again, you see these filaments along which the accretion of material, accretion of stars and gases take place. And slowly, the disk starts to appear. So this is an edge-on view, and so you see that slowly and slowly disks start to appear, and it starts growing in size due to this accretion and so on. And now you have some structure coming in over here. Uh, this is not a simulation that I ran. Of course, it's from the TNG50 Illustrious TNG collaboration, if you've heard of them. But these movies are publicly available. So you see some material comes in and it merges and accreting into the galaxy. The disk gets perturbed. And all of this is happening. So the other point to take away is also the Milky Way, or the galaxies in general, they are not static, smooth distribution of matter. They are quite dynamic. They are hardly in equilibrium and so on. So it's a very dynamic process of the formation of the galaxy. Right. So now you have the disk, as I also showed you in the previous videos, in the previous images, sorry. So, right. So this gives you a kind of a broad brush paint understanding of how a typical Milky Way like galaxy forms, right? And it also gives you an idea that, okay, the extent of the galaxy is not only till the disk, till the extent of the disk, there's a huge round of halo and gas stars distributed around the galaxy to much further out extent. Now, these were the models that I spoke of. Now, let's look at the observation.
I
Yes.
guess this TNG50 and all that, they cannot model the formation of the black hole, right, at the center of a galaxy yet, or how is that
Uh,
model?
right. I'm not 100% sure if they can model the black hole or not, because I don't have the full details of the setup of the simulation. But I do know that they do have catalogs of black hole available, or they do take into account the fact that the black holes might be sitting at the very center or even might be distributed around the galaxy. So I do remember that they do have mentioning of black holes in their catalogs, and they do, and the masses of the black holes and how they are distributed and so on. But whether they are put in by hand or whether they get formed
Yeah,
as
that's what I
they
was
play
wondering.
the evolution, yes, that's not I'm 100% sure of. Yep. But yes, it's worthwhile to look at their catalogs, which are publicly available, because they do have information about black holes as well. Right. So these were the models. But talking, and yes, please feel free to ask me questions if you have, because the presentation is not that long. Because of course the idea is not this one-sided communication, but so that you're able to take something interesting out of this 1 hour discussion. Now, talking about the observations of the Milky Way, the first thing to note is that we do not observe the, all the stars or all the structures in the galaxy. In fact, we are limited in the volume till which we make the observations within the galaxy. So, what I'm showing you is the blue. What you're seeing is the distribution of stars. So that's in XY coordinates and the cylindrical radius in Z coordinates from a simulation. So blue stars are, it's not a real galaxy, it's just a simulation from one of these TNG50 simulations. But in yellow, and the star is the location of the sun, let's say it's 8 kiloparsec away. And by yellow, I'm trying to approximate the volume within which we actually make the observations with the space telescopes like Gaia or SDSS, Apogee, Pan-STARRS, whichever one you know. Um, but of course, this is not a very hard cut or volume limitation of the surveys. Of course, if you have very bright objects like star clusters in the halo, globular clusters, or very bright stars, you measure them as well. But over 90% of stars or 95% of stars that you observe are kind of within this very restricted volume. So that's one of the limitations that the observations have, and that's simply because all the telescopes have this faint end limit, below which if you have stars or objects fainter than that limit, we fail to observe them. So then one thing that should not come as a surprise to you maybe is that we have the measurements of majorly, mostly only of this region of the Milky Way, but we are trying to understand the global distribution of matter, the global processes of formation, how the formation takes place, and so on. So this becomes a very challenging task, right? So that's one. The second thing is probably also to make you realize that we are making these observations from the heliocentric frame, which is also rotating, and our 60 coordinates, 60 phase space information of the stars are not simply the 3D XYZ and 3D VXVYVZ that we have in general in classroom setting and so on. So all the measurements are being taken from the heliocentric frame, another important thing to keep in mind. And so our 3D position of a star, let's say, they are measured in terms of longitude. So please go back to your high school physics or bachelor days where we studied the spherical coordinates. So you have this angle going from 0 to 360 degree, then you have the latitude minus 90 to plus 90 that covers the entire sky, the 4 pi of entire sky. Then you have the parallax that approximately gives you the distance of the star. So all of these measurements are being made by Gaia as we speak. So this gives the 3D position. Then you have the velocities in terms of proper motion. So proper motion is something we call on-sky angular velocities. And then you have the line of sight velocity. So this is what we get. But of course, uh, we can only better understand if we have the measurements from the center of the galaxy, which we can then do. So we can have these measurements and we can transform them in galactocentric Cartesian coordinates x and b and so on. So this transformation is of course possible because we can of course better understand the system if we have a point of view for it from the origin of the from the center of the system, and the system being galaxy for us. So now this is what the Milky Way looks like. So until now, all the images that I was showing you were either artistic impression of the Milky Way or simulations or models. This is the actual observation of the galaxy, right? So this is a map produced by the Gaia collaboration, which is Gaia is a space telescope launched by European Space Agency in 2013. Since then, it's been mapping the sky. So this is how the full 4 pi sky looks like uh, when viewed by Gaia. So now remember that we are in the sun's frame, right? So at the very head on, we have the bulge that I previously mentioned. So you're seeing these stars, then you see this disk, stellar disk distribution, and then above and below, you kind of see this distribution of sparsely population of stars, which is basically the halo of the galaxy. And then if you're wondering about these two structures, they are basically large Magellanic and small Magellanic clouds. So this is how the galaxy looks like in the space of the measurements. Here I'm showing you how the proper motion of these stars, so the angular velocities of these stars on the sky look like. This was again another video released by the ESA collaboration. And so these stars are integrated forward in time, and you can see these minute motions of stars. So of course, stars that are closer to us seem to be moving at higher speeds. The ones further out into the halo or distant from us, they have smaller speeds because these are angular velocities. So of course they change with the distance. So this is just to give you a flavor of what kind of measurements we are dealing
Yes,
with.
sir.
Yep.
How can you differentiate between the stars and the stars in the whole thing?
Can you
Uh,
repeat the question? Yeah, even I couldn't hear it.
Okay, sir.
Yeah,
Okay.
Mushtala,
Okay, sir.
can you repeat? You're muted now. Or maybe write it in the chat if you're having
Yeah,
some
yeah. I'll
troubles
write it in the
this
chat, sir.
thing.
It's not.
Okay, fine.
okay.
You can go
Right.
ahead. Yeah.
Yep. So this is just to give you a flavor of what models we have and what kind of observations we have, and then we can start comparing these two. So returning so I know that you might be feeling I'm kind of derailing with the Shiva and Shakti discussion, but that's exactly what I'm coming at. So now coming back to the our original question of interest, that how did the Milky Way halo form? So from models, we have this understanding that you had very smaller galaxies that came in and merged into the Milky Way, and these smaller galaxies, they kind of got stripped, disrupted by the potential of the galaxy. And here you are seeing some of these galaxies merging. This is a simulation. Each galaxy, smaller galaxies, color coded differently, and slowly the halo was built by accreting and merging of these smaller galaxies, and then stars got dispersed and distributed in the phase space of the galaxy. And this process kind of went on for the last 13 gigayears, and so throughout the evolution of the Milky Way. So this is then, if we look at the, let's say, XY space of our galaxy, the Cartesian XY, this is what we kind of expect, that if we want to understand how the halo formed, then this is what the distribution looks like. And of course, it is very structured because of the same reasons that I also showed you before, that it's not, galaxy is not a smooth distribution of stars. There's highly structuredness because it's formed by these subcomponents, by these smaller and smaller galaxies. But this is again a simulation, right? Where I'm the god of the simulation. I know the initial conditions. I know everything which star came from which star. So I can color code them differently and see how they look like. But in observations, that is unknown. That is exactly what we want to know. But you can also see that if these stars are basically indistinguishable in this XY space, right? Because they are overlapping, they are phase mixed. So then it becomes hard to disentangle them into different groups, because if I have a given set of stars, I want to be able to distinguish between different stars that came into different groups or different mergers. And so what we do is that we take the Cartesian, the 60 phase-space measurements of stars, and we can map them in the LZ and E space. So in the space of Z component of angular momentum and the energy. And the hope is that in the space, once you transform these star particles into the space, then stars that came into different merger, they would end up occupying different spaces in this angular momentum and energy space, the LZE space. And that's simply because stars that came into a given merger would have come along a very specific unique orbit. So all of those stars would end up having very same orbit even throughout their evolution, and LZ and E are conserved in an axisymmetric potential, right? So for instance, this is what the galaxy looks like in the cylindrical R and Z component, and you can see that there's a symmetry along the z-axis because there's a disk. Otherwise, it's the galaxy is just a spheric, most approximately a spherical halo, except due to the presence of the disk, it becomes axisymmetric. And we know from the bachelor days, maybe from also from the high school days, not sure, that the z component of angular momentum and the energy are conserved. They are constant of motions for an axisymmetric potential. And so if you had a bunch of stars from a given merger coming along a specific orbit, and then you have another merger stars coming from a different orbit, they would end up having retaining the same values of LZ and E, and therefore they would form these groupings that I'm showing you here. So these are, of course, conceptual diagrams right now to make
So
this.
just a naive question. I mean, so my understanding, since most of the mass of a galaxy is made up of dark matter, right? So shouldn't they be affected by the halo of the dark matter halo, which is spherical instead of the disk?
Yes, so I mean, so when we talk about the potential of the galaxy, no, okay, are you asking that? I understand. So the thing is that when we are talking about the potential of the galaxy, using which we compute the energy, for instance, so we account for the mass distribution of the disk, the mass distribution of the bulge, and the mass distribution of the halo. So once you have the merger coming in and it's going about the galaxy, then it's evolving in the potential of the disk and also that of the halo, right? So let's imagine a scenario where we had no disk. It was just an approximately spherical distribution of stars and dark matter halo. Then the total angular momentum and the energy would be conserved, because we know that in a perfectly spherical potential, the capital L and the E are conserved. But because of the presence of the disk, mostly, the Milky Way potential ends up being axisymmetric. So not the total potential, but just the Z component
Okay,
of
okay,
potential ends up being conserved, if it makes sense.
okay, okay, okay. So,
Yep. But yes, good question. Um, Right. So then this means if we want to identify these mergers, these groupings that basically built the halo. So slowly and slowly, maybe you're trying to see I'm coming towards the discussion of Shiva and Shakti. So if we want to identify these mergers using the present day distribution of stars, then I should look at the LZ and E space. So how does the LZ and E space for the Milky Way looks like? So I have taken, so here I'm showing you the actual observations. So you have the 60 phase space measurements of all the stars in the galaxy from Gaia, and you can map them easily in the LZ and energy space. So this is an actual, based on actual measurements. So LZ, you can easily compute by your R cross V, the Z component of R cross V. So R is something you're getting from Gaia directly. V is something Gaia is measuring for you. For the E, while the kinetic energy is something you can still get from Gaia, the phi, as Shantanu and I we were discussing, is something, is a model of the Milky Way, the total galactic potential of the Milky Way that you need to assume. And it is this phi model which basically is axisymmetric. And so, right. And so let's try to understand just a little bit what this LZ and E space is and why does it look like the way it does. And for reference, I'm also showing you the measurement of the sun here in this stuff. So you have three major components in the galaxy. You have the stellar disk, you have the stellar bulge, and you have the stellar halo, this sparsely distribution of stars around the galaxy. So this is where most of the bulge stars end up being. So of course they have lower energy because at the very central regions of the bulge is where the potential is highest. So there the energy ends up being most negative because that's where the most bound particles of the galaxy are at the very central regions. Then this overdensity of stars. So this is a density diagram. This is a 2D histogram. This overdensity of stars that you're seeing here is disk. And why does it end up in in this kind of shape is because this is called the line of circularity. All of these stars tracing this line over here basically lie in they're restricted to the plane of the disk, right? So if we know that the way the sun is moving around the galaxy, it's very much restricted in the plane of the disk. So it's just going round about that, and which means it only has a z component of angular momentum, doesn't have lx or ly. It's just the z component of angular momentum, right? And so if you just do the math, 8 kiloparsec times 230 kilometer per second, you would basically end up at a value around minus 1800. And what minus and plus means, minus means you are moving in the direction of the disk, plus means you're moving in the direction opposite to the disk. So for instance, this bit over here would basically mean a star that has motion exactly opposite to that of the sun. So another star over here restricted in the plane, but it's moving in the direction opposite to the disk. But slowly and slowly, as you look at the other stars which are not restricted in the disk, in the plane of the disk, the stars can have orbits going like that, whichever direction. So you end up reaching in the region of the halo. So stars in the halo end up having eccentric orbits or all kinds of orbits which are not restricted to the plane, of course. So for instance, a star over here which has LZ equals 0. So all of these stars which have LZ 0, that means they only have the radial component, which means they're just going in and out. They have no rotation component. Their LZ is 0. They're just going radially in and out like that, be it like that, be it like that, doesn't matter, right? So this is just to roughly understand how the why the LZE space looks like the way it does. But the major idea is that this is where most of the disk stars end up being, and this is where most of the stars in the halo surrounding the galaxy, they end up being, right? Now here, what I've done is that I've also taken into account the metallicity of all the stars. Uh, Again, to highlight that the chemical composition of the stars in the disk are very different than that in the halo. Or the metallicity of the stellar disk is different than that of the halo. So stars in the disk are quite metal rich, and that's why they have this red color. And sun is also itself is also quite metal rich compared to the halo where stars can have are quite metal poor, can have chemical composition as low as minus 1.5, minus 2, and so on. So this is just roughly looking at the LZE space, also counting for the chemical composition. So we have all these measurements for millions of stars in our galaxy. But again, coming back to the question, our final agenda is to try and find those overdensity of stars, because in this LZ and E space, if we can find those overdensity of stars, then that would mean that those are the mergers that came into the galaxy at some point. So we're interested to find those overdensities in this space. And this is where our paper
So just
becomes
before you
interesting.
go ahead, very naive question. So I guess our whole galaxy is also moving towards Andromeda. Okay, so does that make any difference, or in that case, we just consider a whole sort of Milky Way as some sort of an inertial system, and then nothing changes?
Could you please say again the first sentence? Our
Yeah, yeah.
whole
So our whole
galaxy is
galaxy
moving.
is moving towards Andromeda, right? So I mean, does that make any difference to the angular momentum and the energy?
Right. So Andromeda and Milky Way, they are kind of coming together. That would for the scope of this study, it would not make much of a difference. But it's a very interesting question because these LMC, this very massive LMC system that you're seeing here, the recent studies have shown that LMC might be perturbing the Milky Way, which means this phi, which I just called axis symmetric, might not be axis symmetric, and it's time independent because Milky Way right now is kind of attracting LMC towards it. And LMC is much closer by at a distance of about 50 kiloparsec. Andromeda is still further out at a distance of about 700 kiloparsec, I think. But LMC is much closer, so and it's quite massive, so it's kind of perturbing the potential. So potential being time ends up being time independent. So in principle, the potential of the galaxy, our galaxy, it's non-axis symmetric and time dependent, but we need to make certain approximations to kind of simplify the study. But I doubt that even if the potential, if we choose a very realistic model of the potential, which is time dependent and so on with all the complexities, the result that I'm about to share would still hold valid.
Okay.
But yes, in reality, this was just to give you a very basic understanding and basic kind of assumptions that we make about the galaxy. Because of course, I mean, talking about this figure that I just showed you, that LZ and E is basically nearly constant of time. That's not true, because from since the beginning of the galaxy, the mass of the galaxy would have grown, which means the potential is changing, which means the energy is, of course, not remaining constant, right? But at least for the past 6, 7 billion years ago, maybe it was mostly constant. But this is just the kind of approximations uh, we make most of the times to have at least the first approximation understanding of the things we have. And then, of course, later on, we can add more and more complexities if it kind of broadly addresses your question.
Okay, thank you.
Yep. I hope I didn't confuse you more,
No, that's fine.
but yes. Yes, so this is where our result comes into the picture. So this was a study carried out by Hans Walter and myself. So Hans Walter, he's a director at the Max Planck Institute of Astronomy in Heidelberg, and this is exactly what we did. So we are trying. Our aim is to now look at use this LZ and E space and try to look for groupings of stars. So this is exactly the same plot that I showed you before. But the another thing we did is that we tried to split up this LZE space in the metallicity bins. And that's only because we expect that stars originating from a given merger from a given smaller galaxy would have very specific chemical composition compared to a compared to a stellar population originating from another mergers, because they had different evolutionary history, different mergers would have, depending on their masses, different gas reservoirs. So their chemical enrichment, chemical composition of the stars in different mergers would be somewhat different, if not very different. So then we try to split up in the metallicity space, and then you see this. So this panel corresponds to metallicity between minus 0.5 and 0. Here it's minus 1 and minus 0.5. So as you go all the way down, you're basically decreasing in metallicities of these stars, right? So the main takeaway from this is that these two panels, where I'm showing you only those stars that have metallicity between minus 1 to 0, you see that the disk appears, right? Stars in the disk, they mostly appear, and that's because, as I previously mentioned, because the stars in the disk are quite metal rich, and that's also one of the reasons we dubbed them to be slightly younger in age, for instance. And then these three panels, where the metallicity ranges from minus 1 to until below minus 2, we see some of the very interesting overdensities appearing, right? So we see, for instance, sausage enceladus. That's a previously identified overdensity, merger overdensity. It was identified in 2018. Then you have the poor old heart. This was identified in 2022. But in this particular study, we identified two previously unseen overdensities. One you're seeing here in this LZ space, and another one here. And they are also seen in a much lower metallicity bin. So you're seeing some remnants also here. That just means that most of the stars in these two populations have metallicities between minus 1.5 and minus 1, and you have less number of lower metallicity stars. So this is exactly what we then dub. We refer to these stellar populations, these two overdensity of stellar populations, as Shiva and Shakti. And that's exactly what I showed you in the
Maybe I
very
missed
first
this.
slide.
So what about the spatial locations? They are in the disk, and how far are
Right.
they from the sun?
Yep. So that's a good question, because you're seeing that the LZ and E of these things, they kind of are quite very close to the disk. Then is it that these stellar populations are lying in the disk, but they are quite different. Their distribution and orbits are quite different from that of the disk. So I'll have to go a bit further for that.
Okay, fine. If you're going to come to it,
But
yeah.
that's fine. But that's fine. I think I should have included this plot where you asked. So this is to give you a reference for that. So this is again cylindrical the star shown in the cylindrical coordinate and the in the Z coordinate. So these are Shakti stars. These are Shiva stars. And if you know that the scale length of the disk in terms of height is about 1 kiloparsec, right? So the disk is kind of restricted within this 1 kiloparsec of the z-axis. Then the fact that these Shakti and Shiva stars, they are distributed, they are spanning distances much larger than that, means that they don't have disk-like orbits. They have slightly halo-like orbits. This thing over here is sun, location of the sun, right? So of course the distribution of the disk is somewhat restricted within this plane, galactic plane, but you have stars both up and down. So yes, so I understand that this question is arising because these seem to be kind of very close located in the regions that overlap with the disk, but this is a very large space, so they are not exactly overlapping with the disk. This difference, this small difference, becomes quite significant in terms of phase space, right? So yes, but it's a good question. Um, Yes, so and since this is exactly what we did, we made these box selections. These over densities are quite obvious. We made these box selections, and then this is how the distribution of stars look like, as I showed you in the first slide. But this is about the dynamics of these stars, right? So how they are distributed in the galaxy, what their orbits are like, and so on. So their motion tend to be in the direction along with that of disk, but they are not in the plane of the disk, right? Yes. So now talking about the chemistry of these stars, which is again a very subtle and complex topic to touch about, but I'll just dedicate 2 slides to this. So please bear with me, and we are almost towards the end of the presentation, because these are the 2 aspects we study for Shakti and Shiva: their orbits and dynamics, of course, of these stars, but we also studied their the chemistry of these stars. So before bringing up Shakti and Shiva, the chemistry of Shakti and Shiva, let me just give you this conceptual understanding about the. So on the x-axis we have the metallicity of stars, on the y-axis we have the abundances of stars. So by metallicity I mean Fe over H, the abundance I mean the alpha elements over Fe, aluminium over Fe, magnesium over Fe, or all of those elements basically. And so the general understanding is that if you have stars in a that were born in a very massive system. So, for instance, the disk stars being born in the massive Milky Way like system. So, Milky Way is a massive system. Then these stars, which are born in very massive progenitors, they end up having higher metallicity and also higher abundances, which are shown here in the red. And that's simply because these massive progenitors, because they're massive and dense, so the gases inside these massive progenitors were cooked in this high pressure system, and because of this high pressure cooking, they end up producing more elements, higher order elements, and more metallicity, and so on. Along the
There's
same
a
side,
question.
yep,
I'll just read it aloud. Why is the
sure.
concentration of stellar distribution of both Shakti and Shiva located at left side of the galactic bulb?
Right, that's a good question, and that is because of the reason of this, right? So for instance, here I'm trying to show the volume within which we are kind of restricted by the observation. So in this plot, the center of the galaxy is over here, and the sun is over here, but we are kind of restricted in this region of observation because stars further, which are very distant from us, we don't observe them in Gaia or any other astrophysical survey because they end up being faint. So if you have a same star, you take it at a very large distance, it will become very faint. It will not be observed by the telescope. And ideally, Shakti and Shiva, we understand them to be distributed kind of evenly around the center of the galaxy, but we end up observing only those stars in this region, right? And that's why in Shiva and Shakti distribution, we kind of see this cutoff that no stars are observed in this region. And that's only because the telescope itself doesn't observe those stars, if it makes sense.
Is it clear,
Okay. But,
Niharika? You can ask again at the end if you have follow-up
mhm.
questions. Yeah, please go ahead. That's okay.
Yep. Right. Okay, yes, so that was for the massive progenitors. More massive progenitors, higher density and mass. The gas is cooked under this high pressure, so more elements are formed, and that's why it ends up in this high metallicity, high element abundance space. On the same side, on the other side, if you have a smaller progenitor, like a dwarf galaxy, like a small galaxy, where it has less mass and that's why it has less density. So the gas is not very pressure cooked; it's only slightly pressure cooked, and it ends up producing lower order elements and higher order chemicals. Ends up being metal poor and ends up being deficient in elements like aluminium, magnesium, and all of that. So that's the generic understanding. What's interesting about Shiva and Shakti is that while they are poor in metallicity, they have higher abundance, right? So that kinds of gives an impression that yes, while they were quite massive systems, but the chemical evolution in these progenitors of Shiva and Shakti kind of took place a bit differently than how it takes place in Milky Way or other dwarf galaxies that we observe around the galaxy. So this is something we are still trying to understand, but it's something that I just wanted to point out, right? Because we have so far we have observed this. I'm showing you the LZE space of the galaxy, and I'm showing you different stars. Each point is a star, and they belong to different mergers that we have identified so far. And you can see Shakti stars over here and Shiva stars over here. So this is one of the characteristics that distinguishes Shakti and Shiva from all the other mergers of the galaxy, which is mostly this very interesting insight about the chemistry that while they are metal poor, they are also enriched in metallicity, in abundance, sorry. And so this was more of a conceptual diagram. This is, I'm showing you a more formal diagram, which might look a bit complex, but each point over here corresponds to the star. So blue means Shiva stars, magenta means Shakti stars, green means the star from the sausage Enceladus. So that happens to be one of these dwarf galaxy mergers. And then this is the stars from the Milky Way disk. So you see that just very quickly, not to confuse you very much, but I might end up confusing you, is that so these stars over here are from the disk of the Milky Way, and these end up being metal rich and also enriched in alpha elements, alpha over Fe. And then these are dwarf galaxy stars in green, metal poor, and also kind of poor in alpha abundance. And then this is where Shiva and Shakti are, which are kind of metal poor, but they are more enriched than these green stellar distribution, right? And this was kind of the point I was trying to make in this more conceptually understandable, obvious diagram. And then this is similar. Similarly, we see it. This was in the alpha elements. This is something we see in magnesium elements and aluminium elements and so on. So this kind of suggests that okay, Shakti and Shiva had quite an interesting evolution in terms of quite interesting chemical evolution of stars took place in Shiva and Shakti. And I think this I've already shown you this diagram. This was kind of a summary diagram that we created, where basically all the mergers that we have detected so far in the LZE space are kind of plotted here. So Sagittarius, maybe you're aware of this, that there's a stream of stars wrapping around the galaxy that's called Sagittarius stream, and those stars are plotted here. Sagittarius stream was discovered in nearly 2000, but since Gaia, we have been able to discover lots of more of these merger stars, Sequoia, Thamnos, Pontus in 2022, and so on. And with time, we are discovering more and more of these mergers that kind of built the galactic halo, as I was talking about. Yes, so that's all from my side. And I thank you so much for your attention. And yes, if there are questions or anything, happy to answer.
Yeah. Yeah. So thanks a lot, Khyati, for a very interesting talk. I'm still trying to digest a lot of these results. I think very interesting. So questions. So please raise your hands. So, and then I'll get to you. So students, yeah, please don't feel shy. Please ask. Okay.
Yes, and your questions, sorry, your questions could be very specific to Shakti and Shiva or in general about this field, because as I said that it's, if you could get excited a bit about this field as well, that's also nice. I hope I didn't end up confusing you, or okay, maybe students are thinking, okay, this is a field I will never work on. So, but
Yeah.
yes.
So I think Balakishore, you had a question during the talk. If you can speak now, you can ask it now. Yeah, please ask. Okay, I still cannot hear. Maybe you can just type. Okay. So let me ask questions. I guess yeah, your starting point is Gaia data, and probably that this is a whole separate talk in itself. So how do you get energy and LZ from just the Gaia measurement? I presume you must need dynamical models also, right?
Right. So, right. So coming back, that's a very good question and fundamental question. So Gaia is providing us LB, parallax, and mu L, mu B, and V loss. So of course, the 3D positions can be obtained by simply multiplying this distance with B and L, right? So the distance with the I mean, so before the first step is to convert this heliocentric uh, measurements of stars into the galactocentric X and V. That's the first step. And that, I think, if you can visualize, we can assume the distance of the sun from the center, we can assume the velocity of the sun. So we have these two measurements, and based on this, we can translate LB parallax and mu L mu B V loss into this galactocentric frame using simple trigonometry. So you have these trigonometric formulas, you can apply them and you can get this. So these trigonometric formulas are available in, I think, yes, astronomy textbooks, or maybe there are Python packages that also allow you to do this. So you have Python packages like GalPy or Gala. I'm happy to share that with you over email if you want to try out this exercise. Now from X and V, the 3D X, and once you have the for each star, you have the 3D X and you have the 3D V, you feed that information to another Python package, which I choose to be GalPy, but you have Gala, you have GalPy, you have lots of Python packages available, which you can, through which you can do that. But note that LZ is simply R cross V. So it's distance times the velocity. So this is coming directly from Gaia, right? There's no model in this. This is simply the distance times the velocity, which we have from Gaia. The energy, on the other hand, the kinetic energy, which is again half V square, is coming directly from Gaia based on measurement, so no problem. It's the phi that you need to assume, and that we generally assume. So in Python packages, and you have lots of packages available, like I said, you have Gala package, you have GalPy package, pick your favorite. You can now choose your model. So then phi model ends up being something like, right? So your phi is basically, you cannot see it, but please wait. Your total phi ends up being the phi you assume for the bulge, which you could model as, I don't know, spherical distribution or elliptical distribution. The phi you choose for the potential you choose for the bar, the potential model you choose for the disk, and the potential model you choose for the halo. And the way you model it, and these are already given as options in the packages, and that ends up being the phi model. So it's only the energy in which you do that. And you just need to give this information of stars in the form of a table to the package, and the Python package, it spews out the LZ and E values. So yes,
Okay.
it's simple to do that.
Yeah, Kunj.
What does the bar mean?
Sorry?
Like for the phi, you have done it as a
I think that's the baryons, I think.
No,
okay.
so bar means, so Milky Way actually has a bar at the center,
Okay.
right?
Okay.
Yes. So if you look at so many studies have shown this, that can you see my images of this Google
Yes,
images?
yes,
Yeah,
yes.
yeah.
Right? So, for instance, this is again an artistic impression, but this artistic impression has scientific backing, right? So, at the very center of the galaxy, you don't have a smooth spherical component distribution of stars. You have this bar-like feature that you can see over here. So this is what I'm calling the stellar bar. And this is something which is not only observed in the Milky Way, you also observe it in other galaxies that's shown in Wikipedia over here, right? So if you go to, so this is NGC 1300, and where you see this beautiful bar at the center of the galaxy. So this is what I refer to as the stellar bar. But of course, in addition to bar, you also have a bulge. By bulge, I mean a compact distribution of stars, spherical distribution of stars at the center. Plus, you have a stellar disk, which I mentioned, and then the halo, if it makes sense.
Yes.
Okay, yeah, Mushtala Balakishore, you can unmute and ask now. Hopefully, we'll be able to hear you. I think you're unmuted still. Uh, yes. Okay, so I still cannot hear you. So, Balakishore, maybe you just write your question. Okay. Uh, I'll come back to you after that. Okay. So, Johan.
Yeah,
Johan.
yes, sir. So, in the halo of our galaxy, we also see the globular clusters. So, the Shiva and Shakti are part of the stars from globular cluster, or they are different from that?
Uh, they are uh, they are different from that. So Shiva and Shakti, we understand them to be stars which are originating from one of these merging galaxies. So as I mentioned in the talk, that's our understanding that initially there was these smaller galaxies of stars. So they had these galaxies also had stellar population that fell into the Milky Way. They end up disrupting because of the gravitational potential of everything. They end up these smaller galaxies end up depositing their contents into the Milky Way. And so we believe that this is where the stars of the Shiva and Shakti are coming in. However, these smaller galaxies that came in, inside these smaller galaxies, there could have been globular clusters as well, right? Because the globular clusters are not only present in the Milky Way, they are present in many other galaxies, both more galaxies more massive than Milky Way, galaxies less massive than Milky Way. So maybe there were globular clusters inside these galaxies that also came in, end up populating the Milky Way. And in fact, we do find some of the globular clusters that lie in the similar that have similar orbits as that of Shiva and Shakti stars. So you can imagine if you have the 60 phase space measurements of all the globular clusters, you can plot them in this LZE space. And so we find that there are a few globular clusters that lie overlap with this Shakti region and with Shiva region, means those globular clusters have orbits similar to Shakti and Shiva stars, which means that maybe they came inside the parent galaxy of Shakti and Shiva, if it makes sense. But Shakti and Shiva themselves, per se, they are not formed by globular stars from disrupting globular clusters.
Thank you.
Okay, Ambika.
Yeah, so thanks for the nice talk. I have two questions actually. So the first one, since you mentioned bars, so I was wondering what is the difference between the how a bar spiral galaxy is formed with respect to a regular one. So I'm aware that these spiral galaxies consist of arms, which are basically density waves which are moving around the galactic center. But is there anything fundamentally different in the way that these form, these two different kinds?
Yes, so that's a very interesting question. The formation, these are actually the cutting edge research topics that are happening right now. I know in India, in Europe, in America, Canada, everywhere. We still do not understand how do bars form in the galaxies. We still do not have 100% understanding of how do spiral arms form in the galaxies. So these are Ambika, right? If I heard it correct. So these
Yes.
are really the questions at the very frontiers which people are now trying to understand. And if you could, let's say you go down this field, right, and you try to understand this, and you come up with an understanding, then this would be a huge help to this field in general itself. But again, in this regard, I should say that the presence of the bar make the potential non-axis symmetric because the bar is rotating, so the potential does not end up being axis symmetric anymore. But that's just an approximation that we make for the study. It's a reasonable approximation. But yes, there's not full complete understanding of how bars and spiral arms form yet. But this is something we observe in the simulations as well. And this is something we observe when we observe Milky Way or other galaxies as well. But it's a genuine question that how do they form? We do not know. It's a good question.
Yeah, Ambika,
Okay.
you had one more question?
Yeah, one more. So I can see in the graph that there are like a fair amount of stars which are having LZ0, but they're still not in the bulge. So like, what does that mean? Does that probably mean that it's moving perpendicular? And how did those stars even come?
Right. So all of these stars that you're seeing here, they are basically just going in and out uh, of the galaxy, and of course, their energy values kind of give you an idea about the amplitude of this oscillation, right? So if you have lower energy, let's say this star over here, it means it's kind of confined within the bulge or the in the region of the bar or the bulge, whatever. It could be going like this within the disk. It could be going perpendicularly. It could be going tangentially. However, its LZ would end up being zero. If you consider a star which has higher energy, then maybe it has higher amplitude right? Because it has more energy, and that basically means that it could probe it. It's probably a star of the belonging to the halo, but except that it has this oscillation. So all of these are not located at the very central regions of the galaxy. These stars would be in the very central regions, but these stars would be going further out into the halo. Could be perpendicular, could be into the plane, could be tangentially. For that, you would have to look at other parameters of the orbit.
Okay. Any more questions, Ambika?
No, that's it. Thank you.
Okay. So
Thank you.
yeah, I'll come back to Balakishor's question. But any other questions? Okay, so let me switch off the recording, and I'll this we still have to we'll still address 1 second. Okay, for some reason I cannot turn off the. Okay, fine. So let me just read. I think Balakishor's question is more general. What research opportunities are available in this field, and how can I start as a fresher to explore this field? Okay, so it's a very
Right.
generic question. Maybe a short reply you can give.
Yes, but Balakrishna, if you can give me context, are you a bachelor student right now? Are you masters? Are you PhDs?
Yeah. Even I don't know the answer.
Uh,
Yeah, Mushtala, if you can type it.
yes, because then it would slightly depend.
Okay.